one of our main goals was to take a photo of Czech Republic. We did multiple photo campaigns and we got one beautiful shot. We basically took a selfie from space of the Czech Aerospace Research Center facility.
In this episode of Inspiring Computing, I speak with Filip, the team lead at the Czech Aerospace Research Center. Filip shares his journey from engineering-focused high school to leading the development of attitude and orbit control systems for satellites. The discussion goes into details and technical challenges and triumphs launching satellites, including their innovative use of MATLAB and MicroPython in satellite control and experimentation. Filip actually emphasizes their success in taking a selfie from space of the Czech Aerospace facility and how this achievement paved the way for future projects. He also explores the complexity of satellite attitude control, the use of CubeSats, and handling limited resources, highlighting the agile, risk-tolerant approach of the research center. The conversation sheds light on the application of advanced computing in aerospace and underlines the importance of balancing innovation with practical constraints. The Inspiring Computing podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world, simulate, explore trade-offs, and gain insights that help companies add more value. In addition to this, we will also be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from. Welcome, Filip, to Inspiring Computing.
Hello.
You are the team lead of the Attitude and Orbit Control System at a research company called Czech Aerospace Research Center. I found this super interesting when I saw your talk at the Technical Computing Camp. I thought to myself, I need to have this guy on my podcast. He is just a powerhouse of knowledge and got wonderful experience. But before we dig into the details of where and how you use MATLAB, Python, and so forth, can you maybe tell me a little bit about what's your superhero origin story? How did you end up in an aerospace research center?
Yeah, so where do I come from? I was at this high school. I was the engineering, more industry specialized high school where we did computers because I liked computers as a young man. And I did a lot of programming, doing my own web pages and stuff like that. And after that, I realized, it's actually not the computer, but the actual hardware, the stuff that moves. So it's like robotics. It really gave me interest, moving stuff, these rovers and all sorts of things. So the natural extension was going to the college that there I was studying. And it was 3 years, 5 years went by. I learned a lot of stuff. And after that, I wondered a lot, where do I go? I'm at the college and what's the trajectory for my life? What do I want to achieve? And there it sparked interest me. I had an interest in business, in creating businesses. So when I had the opportunity during the college to work in a small startup, I jumped at the opportunity. It was a small startup, few people. And what we did is you call it heating, ventilation, air cooling. So it was really cool because then I can see actually what I'm learning in school I can apply. So it was cool to actually go to the customers and see that they are happy that their heating is working properly and they keep the relative humidity in control, and it was good. I finished my college and I went full time on this, and it went 2 years. We pivoted a little bit. We used experience for the climate control, and we started to grow microgreens.
Ooh.
I don't know if you know
that?
what they are. You start from the seed, for example, radish, seeds of the radish or something else, and you start from the seed, and it grows for 1 week or 2, and then you harvest it after 2 weeks. So it's most of the energy comes from the seed, and it's a lot of vitamins inside the seeds. So it's not fully grown vegetable. So it's very concentrated and very healthy. But it needs some specific conditions, and we used our climate control experience to grow this in-house.
Was this kind of a self-serving mechanism that I could buy as an individual that I would buy the seeds and the machinery around it, and 3 days later, I've got the ideal growth for...
We started with serving bigger customers like restaurants and stuff like that. But also locally, you can just order, and 1 week later you would have a order finished, something like that. So you can buy it at your home and serve it during the day.
And then what happens? You go through this journey of creating your company, pivoting, and then what happens?
Then what happened is it was failing to gain traction. Like, we were getting there. It was a very fun experience. But for me, it felt like it was not going anywhere. And we had different opinions with the founder of the company. I got the opportunity to work in aerospace, doing the flight controls for the airplanes at big corporation. So I said, yeah, this is like the experience I need right now. So I jumped at the opportunity, moved to Brno.
Wow, okay. But this is not the Czech Aerospace Research Center.
No, this is another place. It's just at the aerospace company.
Okay, very
Brno.
Good. Flight control?
Yes, I was developer for the flight controls of the bigger aircrafts, like actually carrying. I was exposed at the university first, but this was the first time I saw it actually implemented somewhere.
Okay. And then you landed at the Czech Aerospace Research Center.
No, this is not the end of the journey. I was there for 1 year, and I realized that although I like the job, I don't like being in a big company, like a big company, international, and I didn't like the rigidity of the structures and everything. So I moved to the different startup, not as a founder, but just as an employee of the small startup, like 10 to 15 people. And my task was MATLAB, Simulink, and the goal was to create a simulator and simulation for electric VTOL plane.
So then a VTOL plane, what is that exactly?
Yeah, VTOL is a vertical takeoff landing. So it's like a helicopter that can start and land from one spot. Yeah, and the fact it was electric. It was so really hard. It's like new field. Yeah, after a while, because internally I knew that I want to work in space. And working with the airplanes was a stepping stone for me. Like, this is the closest thing to space that I can do without having big experience and joining big companies around the world. After that, I realized I will be 30 and I want to work in a space industry by the time I turn 30. So this is exactly what happened. And then I joined Czech Aerospace Research Center, and I'm here since.
So I guess for this podcast, is this your own personal opinion, or are you talking on behalf of the company? Do you have any formal statement that you need to tell me about this before we go into what you actually do there?
Yes, all of the opinions are mine, and they don't represent any statement of the Czech Aerospace Research Center.
So now that we got the legalities out of the way, tell me exactly, what is it you do there? On your LinkedIn profile, it says Attitude Orbit and Control System Team Lead. What does that actually mean?
Yes, so maybe I would start with what actually is attitude. So what is a attitude control system? You have a satellite and you want to say, for example, I want to point at this star, like Sirius, for example. And the task of the attitude control is to create a maneuver that will steer the satellite to the location I want to see and stay there. It's pointing, basically. Attitude is a fancy word for pointing.
But maybe to take a step back before we go exactly what that all means. So this research center, so you say you have a satellite, right? But most normal people don't just have a satellite in their back garden. So is this what you do for a living? Is the Czech Research Center send satellites up? Is that what you do?
Yes. To describe a company, we are a research center. We are over 100 years old. I think it's one of the oldest aviation research centers in the world. And right now we have two main things, space and aviation. And I work in the space part.
And space is quite broad, right? Can you help explain it to me who is not in the field or living and breathing it every day?
Yes. Space, what we are focusing is actually creating satellites as it is, like design the satellites that meets the requirements of say there is a customer that wants to have a satellite. They come to us and they say, hey, we want a satellite that does this. And we design a satellite that does exactly this.
I see. And so when I saw you talk, you were talking about the specific satellite, if I remember correctly, the VZ-LUSAT-2 or something.
Yeah,
And
do. Because VZL, just so you know, VZLU is a acronym for Czech Aerospace Research Center. A zkušební letecký ústav. It's very hard to pronounce for non-speakers.
I feel much better now. But effectively, you guys launched the satellite, right? This satellite, it's up there. It's not a simulation. This is a real thing that you launched and is working, right?
Yes, yeah, it's a real thing. We send stuff into space. We don't launch it on our own. No, we use like launch service provider. So, for example, we book a flight, or through our partners, we book a flight on SpaceX Falcon 9, and there it goes on the rideshare missions, where other satellites from other companies fly on rocket launch.
So we need to dig into a couple of things there. So you make it sound like this is super trivial, but it's not that. Conceptually, you could think people send rockets, so how hard is it to send a satellite into space? Apparently, you can't just do it anywhere, so you have to book through specific locations. And I'm guessing, is there a time window, or is this something that you mathematically need to figure out which is the ideal way? How does that actually work?
It's an interesting question, I would say, because there are a lot of topics to cover. I would start actually when we have a customer, they have a need, and what they require to be done, something to be done. Let's say like observing Earth. And we, as specialists in the space industry, select the orbit. And it's depending on the size of the mission, what we want to achieve. Because for the bigger satellites, we have more leeway choosing orbits. But for the smaller, more cheaper missions, we usually opt for these rideshare missions, and they have the orbits.
To see.
So we usually constrain ourselves to the options that are available for the rockets. We select the rockets, and then we design mission around that orbit.
So the presentation you gave, this was, what was the mission exactly? This was also for taking aerial photos.
There were multiple experiments. It was mostly technology demonstration that we are able to do this kind of satellite, because it's a second satellite of VZLU, of the Czech Aerospace Research Center. First one was VZLU, and the goal was to demonstrate the technology we worked on, that we can design and integrate such mission. And we had our own experiments, but there were also so-called payloads. So there were other companies that wanted to test their own devices in space.
Okay.
So, for example, there are some radiation detectors, gamma ray burst detectors, and many more experiments.
I see. But so then that means that you're like integrating. So you had some experiments yourself. You had probably some sensors or some projects that you wanted to try, but you built out a satellite and you had enough space for additional payload that other partners, collaborators could just piggyback onto your work the same way you piggyback onto other. Is that kind of how it works?
Yes, basically. The problem with the instrument, they need to accommodate in our satellite and conform to the platform. You need to have a certain size and certain power consumptions, because these satellites are called CubeSat. It's a certain size standard, so it's easier to integrate. They are usually small, so you have very limited power available. Anything.
So when you say CubeSats, how big is this? Is this like 1 meter by 1 meter?
It's like in use, for example, 1U, 3U units. And 1U unit is 10 by 10 centimeters.
So now I've got a more visual representation that this is actually quite small thing that has to go up into space, right?
Yes, exactly. And it's actually great because this standard allows us to prototype much faster and do the things that normal way would happen 5 years. But there are many off-the-shelf components, so we can do mission in 2 years. We can launch to space from idea to actually integrating.
Oh, and is that how long this project took?
Yeah, it was more complicated with this project, but I think it was something around 2 years.
And what was your mission? Was it to monitor geographic or take photos of the planet, or?
One of the main goals is to take photos of the planet. We had a camera, Earth observation camera, which was pointed to Earth, and we were taking pictures. Also, one of the technology demonstrators there was the attitude control system. Because in order to take a photo of Earth, you need to point.
So now tell me a little bit more about this attitude control system. You said the idea is to point to a star. Most people are probably very familiar with navigation on Earth, and that's very easy. You look at your phone, you have a GPS, you put it in Google Maps or Apple Maps, and you're off to the races. This is not so difficult, and you can get from A to B without much difficulty. How does this actually work in space? So you say attitude is the idea of pointing the satellite in a specific direction. So how does that actually work?
Yes. So you have a set of sensors, and it's depending on your needs, how accurate you want to be in your attitude control. But for the VZLUSA 2, we had magnetometers, which measure Earth's magnetic field. There is a sun sensor, which measures the angle of the sun. It can measure where the sun is related to the satellite's orientation. And as a sensor, we had a gyro. Yeah. It's the same basically gyro as it is in your phone. Yeah. So disclaimer, we're not doing any, although it's a AOCS, attitude and orbit control, we are not so far doing any orbit control.
Okay, that makes life a little bit easier.
Yeah, at the orbital speeds, at low Earth orbits, which is like 500 kilometers above the surface, is around 7.6 kilometers per second. So it's very fast.
Is it cluttered? So my understanding is there's a lot of clutter up there. Is that an issue or not really?
It depends on the orbit. There is a lot of satellites on the low Earth orbit, but also they have the quickest decay. So most of the orbits around these 500 kilometers deorbit within 5-10 years. Okay. They burn up in atmosphere.
What was the lifespan or expected lifespan that you planned for?
We want to make it as our previous satellite. It was almost 6 years in orbit before it burned up, and it was working to the last day, which is one of the longest working CubeSats I know.
Okay. I'm curious a little bit now about this attitude controls. Is it a standard thing that you learn in university, or is this something super difficult? How do you make this happen? You get the information from the sensors, and then you have a few thrusters, I guess. You've got some battery. How does this actually work?
Battery.
Good. You have power.
We have solar panels on the satellite, which provide power. The orbit is 95 minutes, which is 60 minutes on sunlight. So we can charge, and we use batteries when we are in the shade. We don't have a thruster there. And we're using actuators. There are two that actually move the satellite. Main one is reaction. They call it reaction wheel. You can imagine it as a motor with a spinning mass. You apply the Newton's law of action and reaction. If there is no gravity and the motor spins in one direction, then naturally satellite will start spinning in another direction with the proportional force. So this is how you control. You basically have to calculate correct command, correct RPM to move the satellite to point at the thing.
Okay, so this is where the attitude control is coming into play, right? How do you actually build one of these things? Do you have like a simulator, and is this in MATLAB? Is this in Simulink? And what's actually on the cube itself? Can you walk me through a little bit of, I think I understand the maths and the physics. Now, talk to me about the software, and the algorithm and the control strategy here.
Yes. Maybe I will say one curiosity is that this satellite flew only with the orientation to be ready, that software for the control to be integrated, but there was actually none when it launched. So we developed all of our software after the satellite was in orbit. Software for the...
So how's that possible?
Yeah, the satellite doesn't need attitude control. It's designed in such a way that it generates power in most of the directions, so it always gets the power. And it also has the antennas, which can communicate in the satellite. We as I said, we have launched the satellite, and there was no control software. But it also means that the satellite was designed in such a way that it allowed use in a way we could not imagine when we were developing the satellite. We had a Linux computer there, which can run normal programs. One of the companies we were cooperating with They're creating AI models that can recognize patterns, and they were specifically trained, this AI, to recognize clouds in the images. We uploaded their code with the trained AI, and we took a photo campaign. It flagged the photos that had large cloud coverage, and
really?
it worked. Yeah, it was very low coverage.
Okay, so that's this idea of the additional challenge of developing a system as complex as satellite. To develop something with open-ended requirements is also something which is not so easy. So the fact that you've got this in such a way that you could change the requirements downstream and enable new applications that from the time of design was not inspired, created, that's actually unique, right?
Yeah. And it's very tied to the way we do the satellites. We use this standard form factor, CubeSat, and there is a term new space, but we're not bound to any hard requirements. For example, if you take James Webb, which is a very expensive, very big mission, a lot of the things on the line, we have this opportunity to create much more smaller, cheaper satellites. And that way we can also accept more risk. We are more open and more flexible, and we can do stuff that could not imagine. And it's an open requirement. And we have a computing platform in space. And if you want to do something, we can.
That's really special. You must also have a few war stories. So I can't assume that everything worked out very nicely. Do you have a war story that you want to share that you said, oh man, when we turned this thing on, it was pointing always in the opposite direction, and it took us a few weeks to figure out why on earth?
Yeah, I can tell you a few stories like that. For example, there is a certain algorithm before you engage the pointing that slows down the rotation, because sometimes it's spinning too fast for the reaction wheel to be capable of controlling. So you need to slow down the satellite. It's called detumbling. And it's very simple controller, and there is one parameter. And of course, we got some configuration error. And instead of slowing down, it sped up. So it started at 1 degree, 2 degrees per second, and it stopped at 40 degrees per second.
How dangerous is that? If it is a mission critical thing, or is it just, oops, we need to figure out a mathematical way to get this back on track?
Yeah, for the satellite, it was not an issue because there are no appendages, like things flying off. So it was not a problem. It's spinning too fast, and we have a little bit of communication problem because the way it spins, it's too fast. But it didn't pose mission critical error or something like that. That's one of the advantages of these small platforms. They're usually designed such a way that it doesn't require orientation control to be in a nominal, in survivable state. You're still charging and you're still communicating, so it doesn't pose a problem.
Oh no, this is going 40 degrees per second. Does the team panic, or is it like, oh no, we understand what's going on?
Yeah, it's like basically because it's a one parameter, we just flip the sign and it starts working. In control engineering, this is a very common issue, and even bigger satellites can have this problem. So there are very complicated procedures to make sure that, because there are a lot of places that can go wrong, and you need to check each one of those places that it can go wrong and make sure that orientation. So what we have there is a computer which runs a MicroPython interpreter, and there is a file system, and we upload the MicroPython files, and then we execute them. Did it again.
Okay, so there's a couple of very interesting things here. So first you said MicroPython, right? What is the difference between Python and MicroPython?
MicroPython is basically Python, but it's optimized for microcontrollers. It can run small chips and doesn't have any big requirements like normal. So it's more optimized for the devices.
I think most people, when they think of Python, I think they refer to CPython, right? And that's something that you install on your desktop. But what you're talking about is something Python that doesn't need an operating system. Is that it? And it's a slimmed down version of it, correct?
It's very limited to fit in small. I think it can even run on 8-bit devices or something like that with like few kilobytes of memory. So
this is much smaller. But then the idea behind it is that, does it have a garbage collector?
Yes, it does. It has a garbage collector, and it actually creates interesting problems for us, the garbage collectors. because the way we do it, like basically what you do in an algorithm in a control, you have a fixed loop in a fixed rate. Let's say 1 second. So you iterate every 1 second. So you call the garbage collector every one. You can call the garbage collector every loop to clean up each loop. And what we found out, the garbage collector, when it runs, it takes 1.5 seconds. Yeah, so it's like a compromise. What we did, that we don't force garbage collection, and once every 200 seconds it stutters and it collects garbage collector collects the memory, and then it starts again.
I have to ask then, why did you choose for MicroPython in the first place? I would have expected most satellites don't use Python or running on, I don't know, C++, Rust, I don't know. There must be a wide variety of things, but Python isn't the first language that comes to mind when I think of satellites.
These days, Python runs almost everywhere, right? Yes. Why we choose MicroPython? I think the main reason was that it offers us very big flexibility. If I compare it, for example, we have a chips there, some embedded device, and in order to change a program, you need to refresh an entire chip because the stringent budget and time. So the only way there is a bootloader which can reload the C code, which is like core functionalities and everything. But this is actually it's dangerous operation because it can leave your computer not working at all. And second, the image to transfer 0.5 megabyte to orbit for our satellite, it took like multiple weeks.
Yeah. And you're risking no corruption. So you need to be 2000% sure that it's not corrupted, right?
Yes, exactly. So this is why we opted for the MicroPython. And usually the MicroPython, from what I saw, is that it's like the main thing that runs. Instead of running like main in a C, the MicroPython takes place and it runs like, for example, you compile a C code and you flash it. And it's very similar with the MicroPython. You flash my code with a MicroPython core, and then it executes like MicroPython scripts. But what we did is that it runs MicroPython in separate thread on demand. So it only executes when we want it. And the way it does, it loads, we have a file system there, and it loads the script from files.
So let me see if I got that straight. MicroPython, my understanding is it's always running, but it's expecting a main.py or something, a specific file format. And from the moment that file exists, then there's a mechanism and you can set up a watchdog or something that says from the moment that file exists, then you can control that it's working. But that whole process you put on a separate thread, is that it?
Well, not exactly. It's not always running. It starts executing once we say run. So it's like not running at all. It has a dedicated thread, but it's not running unless we say so. And MicroPython, they're like interrupt handlers. So what we basically do is like issue an interrupt when we want to execute it. It receives a signal and it stops itself. Or we can stop the Python code itself and it will just finish it.
So then that's a special thing. So you launch the satellite without having the code. And then after it being in orbit, then you pushed out your first code. And when I say first code, this is the attitude control. So is this literally a Python function or a group of Python functions which have got all the maths of attitude control? Or is it deeper than that?
Yes, I think it's actually now possible, but back then it was not possible to have NumPy, or maybe it would be, but the footprint would be too big because we were running with the issues of having the controller, the memory was full. So we were doing even things like optimizing strings to fit in the memory and like to load it from RAM and stuff like that. So it was very limited space. So we had very bare bones. For example, we were even missing the minimum and maximum functions.
Oh, really?
We had to implement them ourselves. We had a problem, actually a big problem with the floating points because there was not double, only float. For the astronomical functions which are required for attitude control, float was not big enough.
Maybe that's not something I want to do.
There are certain techniques because it's mainly like matrix calculations in the filters, in a Kalman filter. And it can get numerically unstable. So there are techniques how to create UD factorization, which use certain techniques that can make the calculations stable, numeric from the.
Okay. So then, but that effectively means, if I understand correctly, is it all in MicroPython, or do you start in MATLAB and then go to Python and then go to MicroPython? How do you do the maths? Because as a control engineer, I don't remember learning MicroPython. I remember using MATLAB Simulink for these kind of Kalman filters.
Yes, the process I would describe is we prototype in the MATLAB. We do some prototype, some checks, and we connect to the simulator. We have a simulator which is outside of MATLAB. We use open source software for the simulator. Like we use a software called 42 from NASA. It's an open source GitHub repository from one NASA guy. And we connect this to MATLAB and we check that it works. That like our algorithms in MATLAB work as expected. And for the MicroPython route, we basically transfer those algorithms from MATLAB to MicroPython and verify against the simulator again that we did it correctly, that we hand coded correctly, this stuff. And that's like next step to check that everything is okay. And the next step is actually try to execute it on hardware, that we don't have any problems with executions too slow or something not expected because you add hardware in the.
So when you build a satellite, does that mean that you build 3 or 4 of them and one goes up to space and then the other 3 are for the team testing and validating new ideas?
There is a terminology. We use like flight models, which go into space. And then we have engineering models, which stay on the ground. It doesn't have to be exactly the same thing. The main idea behind this, it's behaving as we would expect from real satellite. But for example, it's missing like mechanical structures or some sensors or cameras are not there, like optical instruments, electronics. So it emulates the behavior of.
So if I understand correctly, you start off prototyping in MATLAB, you do your maths and use that as a mathematical guideline. Then you move that into MicroPython, try that in conjunction with hardware, combining the results from the hardware / the simulators, both through MATLAB and MicroPython in the hardware. If they all match up, then you're building up confidence to say that this is ready to be uploaded to the satellite itself in space. Is that how it works?
You got it right.
So then, but maybe there feels like there's a lot of these moving parts. How big are these MicroPython binaries that you send? Is it a binary or is it just a PY file or is it a specific?
Yeah. For the performance reasons, we don't have that on satellite. So we precompile the Py to the bytecode. It's like .mpy in the MicroPython. And these are like binaries that we upload to the satellite. And we section them in such a way, so they're small blocks. We have a few functions coupled together in one file. So if we want to exchange some function, we exchange only one file. And I would say files 1-2 kilobytes per file. And total size would be like 80 kilobytes.
Okay. So that is really squeezing every bit and byte that you possibly can out of this. Okay. So that's maybe not what the average Python programmer thinks, especially if you're doing web apps and things like that. The WebAssembly is, 10 megabytes. Can we do that? Yes or no? You're at a much, much smaller scale here. This obviously sounds like a complex system that you've put together, right? And you alluded that you're doing some maths and you're checking it out and testing it. But can you maybe describe a little bit more clearly, how do you actually test this? So walk me through the different phases that testing happens. And I'm curious of how you actually do testing with MicroPython.
We have a model in MATLAB where we check that the algorithms work against the simulator, that it's pointing the satellite in the right direction. But of course, this is like MATLAB, very abstract representation, and it's not the code that actually executes on the satellite. So what we need to do is we transfer this MATLAB code to Python. So now you have a Python code, but it's actually close to final code, but there is a little bit of overlap. So we write it as a MicroPython code with all of the things. But what we do is we have a Python emulator of the hardware and we run the MicroPython scripts in a normal Python.
Oh,
And that way we can employ PyTest and all sorts of testing, debugging. We can check in the debugger and not be tied to the software or
yeah, because MicroPython doesn't have a debugger built in, right? That's stripped out. And PyTest doesn't work
yeah.
per se. So you have Python, you put MicroPython inside Python.
And the goal is that we execute MicroPython. We don't do any modifications to MicroPython code. So instead, we engineer our Python emulator in such a way that the code doesn't know the difference.
So this is software in the loop testing, right?
Yeah, I think in MicroPython, during the years, it improved a lot. There is also now a package management system in MicroPython that you can, if you have a internet connection, you can download from packages and execute them. Because we focus on the performance and small footprint, this is a solution we came up with. And I would say it works pretty well.
But now I'm curious, when you talk about filters and some control algorithms, there's matrix multiplication. So does this mean that you have to re-implement like very core linear algebra functions in MicroPython, or are there open source libraries that you leverage? Or is this something you just make and say, look, we need this?
Yeah, maybe there are, but we implement it ourselves. So we implemented all the matrix operations, inversions. Like we use, for example, we use quaternions to represent orientations. So we used all the math behind this. We implemented and also conversion between the format. For example, there are multiple ways to represent orientation. One is a quaternion, another is rotation matrix. So we implemented all of these conversions because sometimes it's better to use quaternion, for example, in the control itself, control law. But to represent orientation of the sensor, how it's mounted on the satellite, we usually do this with the rotation matrix. So we need to recalculate back and forth, and we implemented our own like basic math, which we need to deal with.
Okay, so this is a super interesting project. And then this whole idea, so let me see if I get this straight. So you're responsible for the attitude control, right? So you're trying to point it and make sure that the satellite points in the right direction, but more importantly, it's the camera. So when I say little, I'm assuming it's little because your box is small. What kind of resolution can we expect from something 500 kilometers above the Earth?
Our camera, these resolutions, they are so-called ground sampling distance, like GSD, which basically translates is like how big is a pixel if you project it to the ground. And with this satellite, we have a resolution like 40 meters per pixel. So it's not really a big resolution, but it's sufficient to see certain things from space.
Right. So but how do you actually then validate if this is right or wrong? How do you find specific markers with meters by 100 meters that you're calibrating?
One of our main goals was to take a photo of Czech Republic. So we did multiple photo campaigns and we got one beautiful shot. We basically took a selfie from space of the Czech Aerospace Research Center facility. So we took a very beautiful photo when you can see whole Prague, runways of the airport. So that you know that you pointed in the right direction when you recognize the objects. Yeah. When we took the first photos and I was like, oh my God, it's working. And I can recognize the stuff that I'm looking at from the photos that we downloaded from space. It's amazing.
So I guess there's weather conditions that you have to wait and things have to line up. But how long does it actually take from the moment, so the satellite's launched? So how long did it take and maybe how many iterations of uploading new Python binaries did it take before you got to that wonderful photo?
Yeah, there are a lot of conditions. We tried for a half year. If we shoot ground, really like some photo of any ground and not space and edge of the space, we tried half a year to do it naturally and it wouldn't work. It's just because there are some problems with the satellite. So when it flies over Europe, it always wants to align outside, like pointing to space. So we knew we had to do it actively with the attitude control. I would say it took 2 months from the first idea sketch to actually taking these photos. You're right. It depends on the weather conditions. So what we did, we scheduled this for summer when there is less probability.
So then when you take this selfie, is that when the team goes completely crazy and everyone gets promoted? Is that how it worked?
Yeah, it would work like that. But basically, we had this as one of the main objectives
Yeah.
of the mission. And we achieved it within 1 year. So we achieved all of our objectives that we set to ourselves within 1 year
I
of the
see.
mission.
And that's an achievement, right? Because you probably budgeted 1
Yeah.
year and you did it sooner than you expected.
It was sooner than we expected. And it really helped us to gain attraction on different projects, because now we can show like, hey, we are really capable of doing this. We're not just making this up. We really have a proof. So then it got easier to get new projects, like research projects, to develop further things.
You launch it, you achieve your objectives, but then how does it work? Does the whole team move on to the next project? But the thing's still up there, the satellite's up there. I'm assuming you still have some open telemetry that you want to capture and analyze. So does this move to a different team to which monitors and measures and keeps an eye on it? How should I think about that? And is that even public information, or is that hidden away from the world?
It's a tricky. Very usually when we achieve our goals, we move to something else, to different projects, because there are multiple payloads. Others they can focus on their stuff, because really the limitation of the satellite was a downlink bandwidth. So we could run more tests, but it would take a long time to download the data from the tests.
I see.
During the testing development, we started to see issues because it was not launching with actual control software to space. We started to see some issues in our philosophy and design, the way we did things. We took this as a learning lesson to incorporate into our new projects.
You are indeed a research institute, right? So your primary goal is research and to prove that you have the knowledge and you build upon it, right? So there's no shortcuts in this. You have to take years and you keep launching satellites. So I guess you have a few more of these satellites planned downstream that incorporating these lessons learned.
Yeah, the attitude control specifically, it may look easy because we don't use any crazy controllers. We basically do PID control, which is taught at the university, like very basic controllers. So we're not doing any fancy, but it's all the little bits around it that complicates the stuff. And you also have to be very thoughtful about all fields, because there are multiple things that's happening that's affecting the outcome, not only software, hardware. There are issues with thermal. You have cameras, for example. If you want a more precise system, you have a so-called star tracker, which, as it says, tracks stars. So it keeps its own catalog and it sees the stars as a camera. It sees the stars and compares it to catalogs. It's very close to when you navigate on a ship and you look at the stars and you know where the north is and what's the constellations.
Okay, so then, so I think it's very cool that you're using Python, MicroPython. But did you look into maybe like generating C code from MATLAB? So if you're a MATLAB user, Simulink user, based on your experience, you probably came across code generation from the MathWorks tools that is used in aerospace and in automotive for safety critical. Why didn't you go down that path?
So yes, we were looking at our path, and it's actually like what we are updating our process right now to get rid of this hand code and use MATLAB generation to C code. But we don't use Simulink. We use only MATLAB. And we found out it poses some challenges for us to generate, because I would say right now we are moving from this embedded MicroPython environment and we're using FPGA, normal computer, which runs Linux. So it means we don't run MicroPython, we use normal Python. So it's, in some things, it's very easier. We can use NumPy, all the tools. We don't have to develop our own mathematical library because we choose Python for rapid development, and it's easy to develop and fast. But the problem is that the MATLAB generates C. So right now we're exploring the option that we go from C code to actually embed this as a library in a Python and execute C code from MATLAB.
But why then did you choose not to do it directly in C or maybe even Rust? Was that something on the horizon, or is that something you say it's development time is what we're catering for? Or
yes, one of the things is development time, because developing in C takes much more time than developing in Python or Rust. For the embedded controllers we had, it would create a problem. We would need to create some custom linker script to patch only parts of the binary. It can be done, but it also creates a problem how much memory you can erase. So we have memory blocks, and you can erase at the time, and you need to re-upload all the code that you erased. It creates problems like this, which is not a problem for Linux. You can just upload the binary and everything much easier.
I understand.
Maybe, yeah. And you mentioned Rust as well. So this is something we actually looking at right now. But the main reason why we didn't adopt Rust is there was no one that can program in Rust. And right now we hired one guy who knows Rust. So we're not familiar with Rust.
Yeah, so I guess there's a domain knowledge. So as a team, you probably already have a core knowledge around the Python and MATLAB stuff. So you're sticking to what you know best, as opposed to branching out to something.
Yes.
Okay. But on the other hand, you're also a research institute. So I guess it's somewhat your moral responsibility to explore these venues and avenues, even if they may end up in dead ends.
Yes, exactly. But we are a research institute, and we also, when we receive some money, we have some results. We have to have some results, and it's just not that we are researching and nothing comes out of it. We have our goals, and we have to meet the goals we set up. It's not we're doing researching and we can do whatever we want. We are also bound to some boundaries, some budgets, and the results we want to deliver.
So I think the way you articulated, the fact that you're working on a hardware platform, which is not an unlimited budget, that changes some of your decision process, but it also increases some of the engineering elements that you could take for granted, but you don't. And therefore you sharpen your thought process on other elements, which is actually a good exercise, where maybe some people just say, let's throw more money at the problem. You're at a place, no, more money is not always the solution. Maybe we can think about things a little bit better, and how important is float versus non-float and the limitations and things like that. If people want to learn more about you, contact you, or learn more about this project, what is the right way to reach out to you?
Yeah, you can reach me on LinkedIn.
That's it for today's episode. I hope you enjoyed the conversation and found it valuable. If you did, please consider sharing this episode with your friends and family, or anyone who might benefit from it. Also, I'd love to hear your thoughts, so take a moment to leave a review and let me know what you think. And if you haven't already, don't forget to give us a rating. It really helps us reach more people and bring you even more amazing content. Thanks for tuning in, and I'll catch you on the next episode.